So I'll be talking about scientific creativity and really trying to take a theoretical view of this, how to think about fundamental limits, how to approach those limits, and maybe even break limits, which might seem counterintuitive, but I'll get to that. Right? And for most of the talk, I'm going to focus on this idea of combinational or compositional creativity. And if you look at a lot of scientific creativity, it actually does take this form. So Arthur Koestler kind of argued that creation doesn't just appear from thin air, but it's an act where already existing things or ideas are selected and combined or shuffled in a new way. The great kind of theorist of creativity, Margaret Bowden, further said that combinatorial creativity produces unfamiliar combinations of familiar ideas, and it works by making associations between ideas that were previously only indirectly linked. And this is true not just for kind of day-to-day creativity, but even what she calls age creativity, kind of historically important creativity. And so a lot of what I'll describe is focused here. And then at the end, I'll talk about transformational creativity, this idea that you can actually move beyond things that are recombinations of existing ideas. Right? And over the years, we've been able to look at AI for scientific and engineering creativity in a variety of areas. And they often do take this combinatorial form. One example is in protein design. So we had developed some protein language models many years ago. And this eventually led to a startup company called Profluent that Ali Madani is leading that seems to be doing pretty well. Another example is in sustainable building materials. So we developed some technologies to design concrete that has half the embodied carbon as traditional concrete, yet it's roughly the same cost and actually cures faster also. So it helps with schedules. And this was used by Meta at their $1.2 billion data center in DeKalb, Illinois. And now a lot of the hyperscalers, as they're building new data centers, are using our concrete. So Amazon, Google, Meta, et cetera, they've all committed to using this kind of concrete that has half the carbon emissions requirements. And this is especially important because 8% of worldwide carbon emissions are from cement production. So if you have that, it's like taking away all of aviation. Aviation is only 3% of global emissions. Another example is in culinary, and this is actually where I got my start in creativity. So we built what was called the IBM Chef Watson system, and this was for generating novel and flavorful recipes. This was quite a while ago. This was back in 2011, 2012. And again, it's been quite successful. A lot of the things you can buy in grocery stores are actually developed using our technology. So whether it's McCormick's spice mixes or all kinds of other things that are still under NDA. In fact, I think IBM measures the impact just within the first couple of years as between 100 million and $1 billion of impact. So again, not a scientific metric, but it gives an indication that kind of this kind of AI scientific creativity can have societal impact. Another area we've been working in over the years is in wastewater treatment. So one can design unit processes and optimize the performance of treatment plants using various AI techniques. As an example, we're building the second largest biogas plant in India using some of these ideas, right? And so, this has been really compelling for us to actually build these technologies and see them deployed. But it raises the question, what's the best that you could have done? Could you have done better in terms of concrete or culinary or proteins or wastewater and so on, right? And that's the question that engineering theorists like to ask a lot. So what is possible and what is impossible? What are the fundamental limits of building technologies, no matter how clever an engineer you are, no matter whether it's a human being creative or a machine or their combination? And so what we want to do in part is take a page from what at least I think of as Michigan's greatest son. So Claude Shannon, as you may know, he was born here in Gaylord, Michigan, and I grew up in Petoskey and then came down here to Ann Arbor for college and so on. Actually, after the meeting tomorrow, we're doing a road trip up to northern Michigan, so I think we'll do a little pilgrimage to Gaylord on Sunday. And so Broadly speaking, this philosophy of engineering theory is that what every engineer needs is a good set of limit theorems. Um, this is from William Pierce's book, but you might wonder why. Why not just build the things? Why not just build our algorithms? Why do we need to worry about what's possible and impossible? Why don't we just do existence proofs? Um, and there's a variety of reasons why one might care about limit theorems. Um, One is to establish which resources and performance criteria are fundamental and which are largely unimportant. So that's the fundamental part of fundamental limits. So there's certain things that don't matter or don't matter at least currently. And so defining the playing field is one thing that engineering theory helps with. Secondly is to demarcate what's possible from what's impossible. And moreover, providing design insights into operating at that boundary, which is to say optimal designs. Third is to define fundamental benchmarks. And so what you get is an absolute scale rather than just a comparative one. In various industries, like in semiconductors, it's common to say, I'm 100x better than this other thing or 1,000x better. But what would be really compelling, it seems to me, is that we're within 0.000 dB of what's the best that's possible. Right, and so when you're pretty much at optimality, moreover, it kind of states ideals for pushing people to build technologies that approach or achieve those limits. The classic example is in communications. So without Shannon's limits, I'm not sure that people would have invested 50 years of energy in developing our correcting codes that approach the Shannon limit. Okay. And so those are kind of four kind of engineering reasons why fundamental limits seem to be important. I've been working in policy recently over the last few years after the crash course at the White House. And another reason why one would care about limit theorems is also to characterize the probabilities and possibilities of what-if scenarios. Especially when there's deep uncertainty in emerging technology. It's good to know what's impossible from a kind of characterization of policy. So, so what are fundamental limits? I've kind of alluded to Shannon's limits, kind of establishing the limits of communication in the presence of noise. But another classic example is Carnot's limits on the fundamental limit of efficiency of engines. So no matter how clever you are, you can't build an engine that's more efficient than Carnot under the appropriate assumptions. A third example is if you're trying to fly through a forest and you have some certain constraints on maneuverability, then Karaman and Frisoli established a fundamental speed limit of flight in forests without crashing. Sertaj Karaman was actually my roommate in grad school when he was developing this theory, and I was fairly messy in our living room, so I like to take credit for inspiring this work. So. Great. So can we ask ask about a formalism for creativity? And so the standard definition of creativity is something like this: that creativity is the generation of an artifact that's judged to be novel and also to be useful by a suitably knowledgeable social group. And so if we want to develop a mathematical theory of creativity, we want to mathematize these four things: what's an artifact, what's novelty, what's utility, and what's knowledge. And if we can do that, we'll define kind of a closed deductive system in which we can prove theorems. And really that kind of modeling or mathematization step is really critical because that's where that fundamental comes from. So here we're asserting that novelty and utility are kind of the core things we care about. Okay. And since we're restricting ourselves to combinatorial or compositional creativity, I'm going to define components. So we have an atomic unit in the creative domain drawn from the set omega from which artifacts are constructed. So these could be culinary ingredients as an example. And if we're looking at discrete artifacts, we would be looking at the possible combinations of those drawn from the power set 2 to the omega. One can also think about continuous artifacts like proportions of water and gravel and fly ash in concrete, etc. So we're thinking of artifacts as composed of components. Secondly, we have a known set. So these are things that are already known, and some creativity theorists call this the inspiration set. So it's a subset of the possible artifacts, and these are things that are already known. And so in some sense, we have this big conceptual space 2 to the omega, and we have some of it already filled in. And so our space of creativity is the parts that are not filled in. We have a notion of novelty that maps from a given artifact and the inspiration set to measure how surprising this new thing is. An example of a novelty function is the Bayesian surprise, which itself is an interesting information theoretic quantity. It measures how much your beliefs change with the introduction of the new thing. So if I have, I put together, say, like peanut butter and bread and jelly, that's probably not the most novel thing. It matches things that are already in the inspiration set. On the other hand, if I put together whale meat and saffron and sandalwood paste as a culinary dish, that probably is quite novel, right? Because it changes my beliefs about what food is considerably. And then utility is a mapping from the artifacts to the positive reals. Or it can also take the inspiration set into account in certain settings. Okay, so I have these notions of novelty and utility. And now, if I think about an algorithm, it's a lot like the way Shannon described a coding scheme. I can think of it as a probability distribution, a probabilistic process of creating or sampling, right? And so any algorithm actually can be cast as stochastic sampling, possibly degenerately. And so I want to think of kind of having a space. Here, this is a joint histogram of 10,000 possible Caymanian plantain desserts. And what I want to look at is try to find the extremal ones. And that's what I want my probability mass to be concentrated on. Right? Okay. And so as it turns out, there is a fundamental tension between novelty and quality and creativity. And using some ideas from information geometry, what one can show is that this novelty quality trade-off can be expressed as maximizing the expected surprise under a constraint that the quality is at least something over the choice of creativity algorithms. And if our novelty function is actually the Bayesian surprise, the expected value of that is actually Shannon's mutual information. And so the novelty quality trade-off is literally a flipped around version of Shannon's capacity cost function. So this is pretty neat that there's this strong connection between communication and creativity. The limits are the same. And one can kind of characterize this also not just in terms of expected novelty and quality, but in fact in terms of probability of exceeding certain thresholds. So again, using some information geometry techniques, one can characterize the basic trade-off between the surprise being more than lambda s under a constraint that the probability of the quality being more than lambda q over, again, the choice of creativity algorithms. And again, you can kind of get some sense of this in the setting of Bayesian surprise as the novelty function, because that actually is the derivative of mutual information. So you get this kind of KKT condition-like characterization. Okay, so so we have this kind of statistical theory of creativity, which is pretty neat. Like, it tells us what's possible and what's impossible in creativity. But now what we might want to do is actually compare this against creative artifacts. And we've been collaborating recently with James Evans from University of Chicago quite a lot on this question. So how close is human creativity to the fundamental limits? How close is AI creativity to the fundamental limits? And so in statistical theories, one needs probability distributions. On the other hand, when one's doing empirical work, you typically think about novelty as kind of how far different components are from each other in some conceptual space. And so one would want to bridge between these kind of metric notions of creativity to statistical notions of creativity to be able to make this kind of comparison. And what we've kind of figured out is we can draw on ideas from computational geometry to characterize the stochastic sampling. Going back to Beardwood et al., as it turns out, if you throw down IID points in Euclidean space and then look at their combinatorial structures like the traveling salesman tour or the minimum spanning tree, well, first of all, that length converges to something. And moreover, that length of traveling salesman tour converges to Renyi entropy, as shown by Al Hero here at Michigan and others. And in large dimensions, that actually goes to the Shannon entropy. And so what that shows is the kind of these path lengths through conceptual space actually are statistical characterizations of novelty and eventually of creativity. And so what we can do is actually tie things together. And what James has been showing recently is historically there's been growing connections in science among very disparate components. So there's been growing kind of combinatorial creativity of disparate things. So, so this kind of provides a way to characterize that further. Okay, so this is all good, right? We've kind of come up with ways of thinking about the limits of creativity at a fairly abstract level. And now what we want to do is maybe take inspiration from that and build creativity algorithms. And just like one can kind of get inspiration for coding schemes from information theory, you can get ideas for creativity algorithms from this theory of creativity. And so what I want to do secondly is take on this question that's in the title of the session on emergence. And so I want to ask about large language models. So as we're making these bigger and arguably better, what's happening? And is that related to the limits of creativity? So we'll think about this in the setting of LLMs. Okay. So the transformer architectures have certain interesting properties. One can prove that they're universal approximators. You can prove that they're universal computers in the sense of working across domains. You can prove that they're universal predictors in the information theoretic sense, et cetera. But and so those are like kind of interesting findings for sure. But what I want to focus on is that there's these empirical phenomena in training and inference. And can we come up with a unified theory that's inspired by essentially by information theory that explain all of these simultaneously? We want a unified theory that explains the so-called chinchilla compute optimal scaling, that you do need to increase the amount of training data together with the amount of parameters. Secondly, that there is a phase transition, that there's this emergence of capabilities with size scaling. Third, that it seems that after you have this emergence, that there's a plateau. So things don't seem to improve for a while. And those are on the training side. And then also there's been growing interest in inference compute scaling, so-called reasoning, that there's a linear accuracy scaling with logarithmic compute in both training and chain of thought inference. And further, that there's a logarithmic trade-off between training and inference at fixed performance levels in specific regimes. And so we want to develop a kind of a unified theory that explains all of these things. And hopefully it's simple and gives insight. And our starting point for this is some work by Sanjeev Arora and Anirudh Goyal. And so they abstracted what large language models do through this kind of skill mix or skill graph approach. And the basic idea is that you have several skills and they're learned from different pieces of text. And this creates this bipartite graph structure where kind of skills arise from seeing different pieces of text. And further, they did a bunch of experiments, what they call skill mix experiments, that demonstrated the validity of such a modeling approach for large language models. And that, I think it got a lot of press because it was really showing this compositionality of what LLMs actually do. Kind of, they were arguing against, in some sense, the stochastic parrot view of language models. Okay. And so what we did is we built up on that basic skill mix abstraction. And if you're have a coding theory or information theory background, when you see bipartite graphs, it kind of inspires certain connections to low density parity check codes. And so, so what we did was we extended their model slightly to not just have single skills, but to actually have a hierarchy of like a cognitive architecture. But then what we did was a finitary analysis drawing on techniques from the analysis of low-density parity check codes, which themselves are related to various things in statistical physics. Okay. And I won't go through the details in this talk. We can I can talk through those sometime with you if you're interested. But the thing that comes out of that theory is, first of all, that we prove the optimality of the chinchilla size scaling law. not just an empirical finding that that seems to work, but in fact, this is the optimal thing to do, that they need to scale in a linear relationship to one another. Secondly, what we show is that there is this true phase transition. There's this true emergent property. And this is, again, related very much to what happens in error correcting codes. So up to some level of noise, you can decode, and then after that, it fails completely. Right? And so the same kind of thing happens here. And so this is, in some sense, a true phase transition, distinct from what Sanmi Kyojo and others were arguing is kind of a mirage. And then third, drawing on some further ideas in random graph theory, what one can show is that after you have these emergences, there is this plateau, but one can also predict that there is the possibility of multiple emergences. So as you increase the size of these models, you'll have this emergence of capabilities, but then also after a while you can kind of get a second transition and so on. And so there is a little bit more juice left in the scaling, hyperscaling paradigm, even if you think you're at a plateau. Okay, so this has been exciting for us, that this kind of fairly simple kind of model of LLMs seem to reproduce a lot of the empirical phenomena that have been seen. And now there's been growing interest, especially in the last year, on inference compute, so using reasoning. And we were interested in, first of all, extending this type of model to also include inference, but then also explaining things in a unified way, and also further providing kind of resource allocation insights. So as far as we can tell, it's not been clear, should you put more resources into training better pre-trained models, or should you use those resources for doing more inference compute and so on? And so, so we extended the basic model to consider inference time reasoning. And the basic idea is that you want to be able to locate the skills that you've learned in pre-training. And so we cast that as a directed stochastic search over this model's pre-trained skill graph. And we're just finishing up this manuscript, hoping to get it up on archive in the next few days. And one of the things that comes out of this is that you actually want sub-chinchilla scaling once you're taking inference into account. And a variety of other kind of resource allocation ideas that come from this. This matches all the kind of empirical work as well that OpenAI and DeepSeek and others have shown. Okay, so again, we're pretty excited about this as a second piece. So we have kind of a general theory of creativity. What I tried to show you just now is that there's a way to think about inference compute as well as training compute, and they kind of give you insight into the limits of LLMs and transformers in particular. But what one might finally ask is, I tried to say that there's a lot of interest in combinatorial creativity, but where do the parts and their combining rules come from? And so the third piece that I wanted to talk about is a non-neural network technique that we've been developing over the years for knowledge discovery on the one hand, but then also creativity. This is called information lattice learning, and it builds on Shannon's lattice theory of information, which is fairly obscure. He presented it at the 1950 London Symposium on Information Theory, and then it was published in 1953 as like a 2-page or a 3-page document. If you look it up on Google Scholar, it has very, very few citations. 200, but of those, 180 are missed citations that were trying to cite the 1948 paper. So, you know, really only like 20 citations. But it's a really cool theory. And the basic idea is that if you say something in, say, German or in English or in Morse code, if they're valid translations of each other, they're informationally equivalent. They're kind of semantically the same thing. The way he mathematizes that is that if you have two random variables that induce the same sigma algebra, that are causing the same set partitions, then they're equivalent. And once you have set partitions, you actually get all this lattice structure for free. So partition lattices are equivalent to subgroup lattices and in the finite setting and so on. Okay, and moreover, one can prove, as we did recently, that if you use information lattice learning representations together with a certain coding scheme, you can constructively achieve the rate distortion limit for point-to-point, successive refinement, and multiple descriptions under semantic fidelity criteria. So you can achieve actually the Shannon limit for semantic communication, for semantic compression using information lattices. And the kind of the cool thing is that if you have optimal compression techniques, you can make them into optimal generative things quite straightforwardly. You kind of disconnect the encoder and just feed in random stuff, and that'll generate things that are optimal in some sense for creativity. Right? And since this is a foundation models conference, you can also view the information lattice representation as kind of a foundation lattice or a foundation model. So you can take raw data, apply the information lattice transform, if you want to think of it that way. And then in this learned concept space, you can do all kinds of things on top of it, whether it's classification, compression, creativity, et cetera. And so I wanted to show you a little bit about the creativity. So let me do a quick demo as we were discussing at dinner with some folks. So, so the basic idea is you can take, say, music, decompose it into abstract pieces, and then recombine them into new compositions. So this is an existing song that I just pulled up. Right, and so now I'm going to show you some of the pieces that went into it. So this is a melody that's in there. That was Hey Jude by the Beatles. There's Bach's Cello Suite. And again, to emphasize the point, these are abstractions. They're not just tracks from the original. So this is the harmonic structure. Then there's this rhythm. Right, and so now when I put it all back together, so this is right. So that's kind of going down the lattice, this decomposition into pieces, and then I can use that for creativity. So I can let me just take the melody, the harmony from Happy Birthday. Let's say let's do rhythm from Mozart. Instruments like piano, and I'll glue these together. So I get a song like this. Okay, so just a very toy example to give you a feel, and I think I'm running out of time, but I'll just briefly mention that this information lattice approach is very powerful. It's intrinsically interpretable. Every kind of concept is characterized by a group theoretic invariance. There's kind of a computational group theory phase that requires very little data, and then a learning phase from data that requires very little compute. It's human interpretable. You can ask first-year students to convert the output into words, and they can do it really well. And it recovers a lot of known music theory, for example. So about 80% of the music theory curriculum at Illinois recovers new ideas as well. Like Mario likes to tell me that rediscovery is not a big deal, but discovering new things is a big deal. So things like the acceleration of pitch. And it recovers things like gene regulatory networks in genetics, but also discovers new things, does state-of-the-art image classification, performs vision transformers and all kinds of stuff. And we're thinking about some other ideas in scientific discovery using information lattices, whether it's super Yang-Mills theory or quantum experiments or materials. And the hope is that one can actually use this going forward for creativity as well in these scientific fields. So I'll largely stop there, and I didn't get to the breaking limits part, but we have some ideas recently on transformational creativity, which I can tell you about later as well. Right, so just to summarize, what I tried to argue is that there are theoretical limits to creativity that one can approach using information lattice learning. But there's also ways of characterizing LLMs in terms of this unified theory. And we're trying to push from kind of compositional or kind of combinational creativity now towards transformative creativity. And just generally excited to see where science goes, and hopefully we can keep breaking limits.
Very much. It's incredibly fascinating. I'll just ask one question because we have the panel, and I'm sure there'll be more questions coming. I think many of the things that you spoke about are very subjective based on the assumptions, right? There's a bunch of IID assumptions there. And even if you look at, say, Steve Arora's skill mix, there is some implicit notion of orthogonality of the skills, whereas they're not that orthogonal. So how would some of your conclusions change? And I think even for some of the early emergence commentary that came just before GPT-4 and how they were quantifying it, somebody showed they use a different metric and there is no emergence, right, if they change. So the theory is very beautiful, but how subjective are some of the conclusions that you draw?
Yeah. So all theories are, ignore certain things. That's that fundamental part of fundamental limits, right? You keep certain things and ignore certain other things. But I think we, like the skill mix experiments of Aurora and others, as well as certain other empirical things, really do validate the initial assumptions of that theory. And then the predictions that come out actually match a lot of empirical things and also make new predictions. And so those are falsifiable. And so, I don't have $1 trillion to test some of those predictions, but hopefully someone will. They exist. And for example, that IID assumption from the stochastic geometry, that's really for tying the statistical theory to the metric theory. But we're working on extending that and relaxing that. So, things are in the works that hopefully will address some of your questions.
Wait for your talk in SciFM 26, because I think a lot of these things can be taken almost as is and applied to some of the bigger problems.
Yep.
Thank you very much again.
Yep, thank you.